Okay. Okay, let's go on with the introduction of arithmetic datapath. Before they introduce a multiplier, let's have a look at the AND a sub operation on three numbers, such as you want to do AND separation for three numbers of A, B, C. How to do it? Yeah, a simple way is you can use two AND cascade together. So the delay from input to output would be the delay of two AND. Yes. If you want to AND another signal, such as D, so you can do this. Yes, this is the AND for four numbers. So the delay will be three level of a four AND, and you can optimize it. Yes, using the code tree architecture. Yes. Oh, sorry. Let me clear. Let me fix it. Okay. Using the binary tree architecture, the delay will be shorter. Just two level of four AND. Okay, if you can do this, you are on track. You are on track of me. Okay, you have understand what I have introduced before. But the old engineers think more deeply than us. They try to optimize the architecture to make the calculation faster, to minimize the delay. So they invent the carry save AND. The idea is, first, for the AND operation of three inputs, we can AND them up, but not as a whole. We can just AND each 3 bits of the 3 input with the same weight. For example, you can AND the bit 1 of X, Y, Z together using a 1 bit for AND. This is a bit 2, or a bit 2, or a bit 3, or a bit 4. This is or a 1 bit for AND. They are be ANDed parallelly. They are parallelly be ANDed. So this is a delay, just a delay of 1 bit for AND. Then you combine the results. Combine the results to two digits, two numbers. You can combine C to this format, as C has higher weight. Okay, the weight of C1 is 1 bit bigger than S1, so you need to append a 0 to this point, to the bit, to the LSB, and then we combine sum to this number. This is the two numbers we combine from here. Then we use it for AND to AND them up. So you can see the delay here is just 1 bit for AND plus the final for AND. Yes, the final for AND. So this should be much smaller than the 1 for AND. The idea is they just calculate each bit first. You can say this is a 03.02. Yes, 3 to 2 architecture. Change 3 numbers to 2 numbers. Okay, using this architecture, you can get out, or you can figure out the architecture for and observe for many numbers. Yes, you can use this 3 to 2 architecture to cascade them up. All of this is one bit for and operate parallelly. Then you can convert, okay, from the you can small the number of digits level by level. Each level the number of digits will smaller. Then finally you get 2 digits, and use the final and for and to add them up. So this will be an efficient way to do operation on and serve operation on multiple inputs. Well, if you are writing variable code, you just need to write something like that. Okay, you don't need to implement this architecture. The synthesis tool will help you to map your code to such architecture. Okay. Based on this knowledge, we can go on with multiplier. We can go on with the architecture of multiplier. For multiplier, let's take a 4-bit example. Okay, all the 2 input are 4 bits. The first we can call it multiplication. The second is multiplier. So you can say the calculation process is something like that you have learned in your primary school. Okay, just test. If the multiplier is 1, copy it here. If 0, copy 0. Put 0 here. If 1, copy 0 with the right weight placing. Okay, with the right weight placing. So add them up to get the final result. This is the multiply. This is the multiply process you have learned in your primary school. We call these partial products. So basically, for a n-bit multiplier, you will generate a number of partial products, and you have to add the n numbers up to make the final result. The n of n numbers, you can use this architecture. Yes. So based on the add and valence tree, multiplier is easy to implement. But is there any way to improve? Yes. So the valence tree and the final add, it seems this part is hard to improve. Yes. So can we improve this part? Can we minimize the number of partial products? You can say I can choose the minima, which is minima. I can choose the minimum to generate. So for example, if this is 8, this is 4, we can use four partial products. Okay, if this is 16, you can use 8 partial products. Okay, this is okay. Is there any way to further minimize the partial products? So some engineers had thought about it, and they do come out with some solutions. Maybe the man is boost. Okay, maybe the man is boost. So the encoding is called the boost encoding. The idea is try to encode a partial for 2 bits. That is, at this point you will give a partial for 1 bit. Okay, can we combine 2 bits and give a partial for 2 bits? And for example, we want to do this calculation and we encode for bit 1 and bit 0. So the partial should be 0, 1, 2, 3, and these 3 are easy to do. Yes. 0, just a copy of y. 2 times of y is also simple. Append a 0 and then least significant bit. So this is simple to give the partial product for the 2 input bits, but this one is a little tricky. Okay, if you use this doesn't make sense. Yes, so the guy is smart enough. He changed the form to this form. They change to 4 times sub 1 times of y. Minus y is easy to get in digits. You can say it's easy to get for 2's complement encoding of signed number. Yes, 2's complement encoding of signed number. So minus y can be represented as invert all bits of y and plus 1. The plus 1 can easily be done. Yes, you can just append it at this point. Yes. So make them totally a partial. This is easy to do. Okay. So how to deal with the 4 times of y? Okay, he just treat it as a carry in for the next encoding group. Next we will encoding bit 3 through 2. So just treat it as a carry in. Okay, as a carry in. So we just need for the last 2 bits, we just need 0 y here, y here, and we just need 0 here, and for this encoding to uniform, we change the 2 times y to this format. So the carry will be just depend on the value of bit 1. Yes. That is, you can simple the logic. So the carry will just depend on the value of bit 1. So we leave minus 2 times y at this point. Okay. The 2 will be treated as carry in for next encoding group. Okay, let's go on with next encoding group. This is a carry in from bit 1 through 0. This is the value for the higher 2 bits. So this is the same. You can try to understand this table. So this is wide, okay? This is too wide. We just use the same format. Treat this as carry. Leave the 2 here. Okay, this is 1 times 2 times. This is 1 plus 1. Okay, 1 plus 1. This is 2 plus 1. So we just 2 plus 1 leave 1 here, and this is carry. This is 4y. We just leave 0 1 here, and this is carry. So you can say the carry will even we encoding the most significant bit, the carry will only depends on the value of the most significant bit when we encoding. Yes, so this is the logic is simple. This bit is actually bit 1. Yes. So summarize. This is example. This is original 4-bit digital. And if you want to use radius 4 boost encoding, you have to append a 0 and append a 0. Assume this is a carry with 0. So we observe these 3 bits first to generate a partial product. Then we observe these 3 bits to generate a partial product. Then observe these 3 bits. You have to append 2 zeros, 2 bits of zeros. Okay, so you will actually have 3 partial for a 4-bit input. Yeah, you may say the improvement is not big. Okay, you just change 4 to 3, just improve a little. But when you look at the case for a 16-bit digital, this is the case for 16-bit digital. You will find that the input is 16 partial to 9 partials. So this will short the Wallace tree. Yes, the CSA tree. This will give us a simple CSA tree, short the delay and CSA tree. So finally, we get the architecture of multiplier. You have to do boost encoding first, then boost encoding to generate all the partials, then use Wallace tree to convert many partials to 2 digital numbers, then add the 2 digital numbers up to get the final result. This is the architecture of multiplier. Okay, this is the architecture of multiplier for signed number, for unsigned number. For signed number, the architecture is the same. You can figure it out by yourself or look at the book. Okay, from this architecture you can say the delay of the multiplier is bigger than the delay of and a SERP. So is there any way to shorten the delay of the datapath of multiplier? To shorten the delay of, or you can say shorten the delay of any data path. Is there any way? Yes, the most commonly used way is pipeline. Okay, the pipeline. The action we do is insert DFF into the logic gates between on the data path. So let me give you a figure. Assume this is the partial products we have generated. Then we use Wallen's tree to sum them up to get 2 digits, then final for AND. You can insert this line denote DFFs. So you can insert DFFs at this point. Then you will divide the data path to 2 segments, the segment 1 and segment 2. Yes. So each segment the delay is shortened. This is the ideal. For the detail of pipeline, I will introduce it 2 chapters later. The ideal is broken long data path to several pieces of short data path. Okay. For this operation we have learned, there is no need for you to implement the pipeline architecture. You just call the IPs provided by the synthesis tool. Okay, synthesis tool always provides you IPs with configurable functions. You can configure the bits of input at the pipeline stage, such as this is one stage of pipeline. If you are not satisfied, you can pipe it. You can insert DFF at this point. So make it a 2-stage pipeline. Or you can further add pipeline and DFF in the AND itself. Then make it 1, 2, 3, 4. Make it 3 stages of pipeline. So do you know how to pipeline a AND? Can you pipeline an AND? In Verilog, you just write A and B. So how to pipeline an AND? An AND is something can divide or can't divide. Yeah, in C program, okay, you will think the AND is an atom which can't be divided, but in digital circuit you can divide it. Yes. In digital circuit, you can divide the AND. Yes, the AND is made of like something that you can add pipe stage at this stage. Yes. Even for the carrier select, you can add pipe at this stage. Yes, divide the combination logic loop. Oh, sorry, this stage is not very good. Okay, as the delay here and the delay here is not balanced. You have to add pipe register inside this the 4-bit adder. Inside this all these 3 4-bit adder, you have to add pipe registers. Okay. Anyway, the synthesis tool is much more powerful now. You can just instance IPs provided by the synthesis tool and configure the IP with the input you bitwise the bitwise of your data inputs and how many pipe stage you want. Then the synthesis tool will insert the pipe stage and a correct at a correct location. Try to divide the delay of the data path equally. Okay, that's all for multiplier. The next is divider. How to do divider? Yeah, that's it. Okay, you can recall the mathematics teacher told you. You can test the value of the quotient from MSB to LSB using subtractor. Yes, you can test. You can test, for example, sorry, okay. So you can test. This is in decimal format. Okay, let me give you an example in decimal format. So you can test. This can be which number we can give at this point. For decimal, it can be 0 to 9. So this point is 0, and this point 9. Okay. And for digital and for binary, this case is much more simple. Yes, you just have 1 or 0 choice. You just have 2 choices, either 1 or either 0. So you can, yes, that's right. Okay. This is called the test the value of quotation using the subtractor, and you will get the final quotient. You will get the final quotient. So, as I have done before, to calculate the result of quotient, you have to do many times of subtract, and the operation are serial. Yes, the operation is serial. They are not parallel. Yeah, the test of MSB and the test of 1 bit lower than MSB is serial. They are not parallel. So can we improve this? If the process is parallel, such as if you want to do a 16-bit divider, you need subtractor cascade to each other parallelly for 6 times. Yes, so the delay is very big. So can we improve this? Yes, you may think there must be some engineers have invented some method to improve this. But unfortunately, by law, there is no good architecture or algorithm to improve this. So the divider is big, slow, and very, very inefficient. So when you want to use the divider, maybe you can think some other ways. For example, if you want to divide nth power of 2, if the divisor is nth power of 2, you can just use bit shift. You can just use right shift. Yes, right shift. Or you can, if you don't require the accurate, if you don't, you can try this. This is nearly the same. The result of this part and this part is nearly the same. You can change divider to the operation of multiply and shift. This digital must be nth power of 2. So you can use shift, change divider to multiplier and shift. But the results of the two are not exactly the same. Sometimes they are different. there is sometimes there will cause calculation error. If you want to increase the process, if you want to improve the process, so usually you can increase the number. Okay, you can increase this number. For example, now this is nice power of 2. You can try to increase it to 12th power, and this number will be changed. Okay, if the two are not acceptable, you have to use divider. So you can also choose to use the divider IP provided by Synthesis tool. They have different behaviors. Pure combination logic. This is what I have showed before. Divisor, subtractor, cascade together to give the results, and it will give you the results without clock cycle, without clock, doesn't use any clock cycle, just with cell delay. And the pipeline architecture, okay, if the delay is very big, as the delay of divider is very big, we usually use piped. So you can insert pipe registers at this point. This is done by the tool itself. The insertion of pipe register is done automatically by the Synthesis tool, or by the IP, or by the IP itself. Or you can use the tool implementation. Is very expensive in area. The area is very big. You can imagine. The area is very big for the tool implementation, and you can use a multi-cycle behavior. That is, you just give 1 bit of quotient for a single cycle. That is, you just use one subtractor. You just use one subtractor to give 1 bit of quotient. Then for 16-bit divider, you may use 16 cycles to finish the calculation. This is area inefficient. Small area, but use more clock cycles, but use more time. Use more cycles. Okay. These 3 implementation, usually the Synthesis tool will play all these 3 implementations. Okay. Okay, by now, you have learned how to implement all the math functions or arithmetic functions. You may have learned at your 5th year in your primary school. Yes, at your primary school. You can do and sub, multiply, and divide. And these operations are working on integer. Next, we will go on the real number. How to deal with operation of real number. Okay, I will end this section at this point. Okay, I will end this section. Next section will explain how to do operation on real numbers. Thanks.